satellite can transmit anything. You give me whatever you have. I treat them as packetized signal or baseband, right? You give me something, my job is to go over satellite, I return that for you. So it doesn't have to be transport stream, it doesn't have to be IP, it can be IP, can be transport stream, or can be anything. I just treat them as packetized stream. So they introduce something called the generic mode. And how come it suddenly become so good? It's mostly if you want to give power back, you have to have better like error correction scheme. So they use LDPC to replace the Derby and use BCH to replace the red solenoid. This is not something new because this has been invented in 1962 by the MIT professor. I think he still teaches there. Just back then, they cannot realize it. If they want to put, they want to like really process it, they need a full room of computer. It only become possible when the ASIC technology, FPGA technology matured. So you can process the whole thing in a chip and you put in a 1RU equipment. So that's how it became a reality. And also, before we have transport stream, we're always familiar with 188 byte, right? You add 16 byte of a red solenoid, you can also have 204. Now that one is gone. DVB-S2 introduced two block, baseband block. One is called short, it's 16,200 bits. One is called normal, which is 64,800. And later on we'll see why they do it that way. And also they introduced much more FEC reach. And also they use APSK to replace QAM because of the constellation. This is just a quick comparison between this DVB-S and DVB-S2. So modulation-wise, we have two more new one, and raw factor-wise, we have one more. We have 20%. Actually, now people is working very aggressively. 10%, 15% now. It's you see multiple people say that do 15%. Now people do 10%, and very quickly you see people even do 5%. But now we talk to about 4 or 5 satellite operators. The challenge right now is not within the bandwidth. So like all of them have requirement to have channels. If you are not rent the whole transponder, right? And whenever it's multiple carrier in one transponder, then they have a channel spacing requirement. Most of them maintain 25%, and some of them maintain 40%. But if you rent the whole transponder within how you want to shape your carrier, they don't really care. That's when I guess that probably is when people is going to try to push 10%, even 5% raw factor. Then they will save lots of bandwidth. And before it's only one carrier, you only have a single transport stream. Now you can have multiple streams in one carrier. And now the error correction scheme changed. And also before you only have fixed modulation coding. Now you have CCM, VCM, and ACM. So very quickly, we're going to talk about a little bit nitty-gritty. Why DVB-S2 suddenly become so powerful, and why they can have so many new features available. So it all comes down to the change in the building block. So there is no, we keep saying there is no more 188. Now you have this building block, we call it baseband frame. So before 188 bytes, you only have the first sync byte, 47, right? Sync byte. So people know, okay, this is where my transport stream packet starts. Now DVB-S2 introduced something called header. It's 80 bits, and there are lots of information inside. And you have a header. And then you have data field. That's where you can put whatever your packet you have inside. And they also introduced something called padding. So before, if you have continuous like video, right, you can just keep put 188 byte inside, 188 byte inside. At the end, you might not have enough room to put the complete 188. But for video, you might not care, right? If it break, it break. But for some critical data transmission, you might not want to do it because that will increase your packet error rate. So DVB-S2 give you an option. You can do padding, which means you decide how many complete packets you want to put inside. At the end, if you don't have enough room or you don't want to transmit that much, it allows you to do padding to make the whole baseband complete. And that construct your baseband frame, and then you add your BCH, FEC, you add your LDPC, FEC there. This become a complete, they call it a fact frame. So you have two, we mentioned, normal frame and short frame. Normal frame, the invasion, people will use it for video or for continuous data. Because the container is bigger, the efficiency will be higher. Because there is a fixed 80 bits header, right? So you want a bigger container, and then you keep sending it. So this is an invasion for that continuous content or video, such as a video. And also they have short. So 16,200, it's roughly give you a data field of 1,500 bytes. So you can nicely put IP packet inside. So if you want to transmit IP, definitely you can choose this one. So you don't have to break your IP, you can just put it inside. If you go jumbo frame, now people really do jumbo frame, then you can do multiple, put one jumbo frame into multiple S2 baseband frame. But for traditional, most of the IP, this is perfect. Normally you would not go beyond 1,500. So this is a building block now for DVB-S2 transmission. And inside this header, 18 megabits, there are lots of information. So basically, just by reading the header, the modulator will, before the process send it for modulation, they already tell what kind of service it is. It's transport stream service, or it's a generic stream. And it also tells you it's a single stream, or it's multiple stream. And am I going to do CCM, or am I envisioned to do ACM on this content? So lots of information there. And if it's a multiple stream, then the second byte will be enabled. It's called ISI. So it's input stream identifier. Before we know if you have multiple programs you want to transmit, the only way you are going to do is multiplex it. When you multiplex it, you have to use something called pins, right? To associate with different programs. So the recipient, they look at the pins and then they just filter out the content they want. And now with DVB-S2, you don't need that pins. They have something called input string identifier to identify, okay, this baseband frame content belongs to who? And at the end, if that's the one you want to use, you just put the input string identifier there, and then you can filter out the string you want to receive. So that's the key for DVB-S2 to handle multiple streams. And that's also why at the recipient, they can easily separate their string from this multiple string. Just to use a filter called ISI, input string identifier. So this is how this 1 and 0 represent a different meaning of the header. This is the constellation. So after you construct your baseband frame, you do bit mapping to try to convert bits into symbol. So QPSK stays, APSK stays, but 16 APSK, 16 quants, that's what we had before at the DSIG. But the thing is that you look at these 4 constellation points, it's a square. Whenever it's a square, then when you go through transponder, if you want to work in the linear region, then if you saturate, then you have huge distortion. So actually you have to back up. And for NewTek, the only customer we have using 16 points is NASA. From like white sand communicate with space station to transmit video out because they want high data rate. However, they did the test. In order to transmit 16 QAM, you need to back up 7 to 8 dB. That's really a waste of satellite power. However, yes, they got higher data rate. So that's why DVB-S2 get rid of this one, because it doesn't really make, in majority of the application, doesn't make sense to back up so much. So they're replaced with 16 APSK and 32 APSK. Because you have 16 dots, there is no way you put in one ring and the receiver can easily demodulate it. So that will put a huge requirement on the phase noise of the receiver. So they have to put into 2 rings. That's why it's called 16 APSK. A stands for amplitude, because now you have 2 rings, and the ratio between these 2 rings